Greetings everybody, welcome to the last talk for this hall. We'll be having Tim Paine from software engineer at Cubist, and I'd like to say that FPGA is a board. So Tim will be talking to us about building FPGA-based machine learning accelerators in Python. So Tim, we'd like to welcome you on stage. Thank you.
Thank you. Thanks everybody for sticking around for the last section of talks. My name is Tim. I'm a quantitative software developer at Cubist Systematic Strategies, which is the systematic quantitative trading arm of Point72, which is a hedge fund. And I also teach in the computer science department at Columbia University in New York. So I put this up because you're about to find out in like 2 seconds that this talk is full of like company names and manufacturers and things that maybe not everyone is familiar with. So almost all of the things that I'll talk about will have links to their corresponding like homepage or a GitHub repo or something like that. So it will be a little bit of overkill. So feel free to follow along there. I also have to say that I have an academic background in hardware development, but I don't work in full-time in FPGA development or anything like that. I'm predominantly, a hobbyist, and I was kind of motivated to give this talk because of how much the ecosystem had transformed in the past 10 or so years, to the point where, when I had first come out of school and lost access to a lot of the kind of proprietary tools that I had, I wasn't able to do any of these things. But in 2024, I'm hoping that I can motivate everyone and show you that it's not that hard and not that expensive to, learn about these tools, build stuff with these tools, and, learn more about hardware development. So we'll go through a little bit of background. Again, it's going to be a little information overload. I apologize in advance. A little bit of motivation. I have a couple of examples of some machine learning models, and I am not, a machine learning engineer or anything close to that. But a handful of ones I wrote, they're really bad, but they'll demonstrate the point, and a few pre-canned kind of off-the-shelf ones that I'm sure you'll be familiar with. Hopefully, we'll do a live demo of it. I have a few devices plugged in up here, so hopefully they'll continue to work for my talk. And then I'll just do a little kind of brief summary at the end about the state of open source hardware development. So I have a couple of questions here, which is, I'm not going to poll the audience because I can't really see that well. But I'm pretty sure most people here have programmed for CPUs before. I'm pretty sure many people, at the very least, are familiar with something like CUDA programming for GPUs. I think everybody's got like a Raspberry Pi in their drawer that they bought at some point. So maybe they've done a little embedded development, maybe in Arduino or something like that. But I'm willing to bet if I took a survey of how many people have programmed FPGAs before, it would probably be like, maybe once or twice in college. So obviously like CPU, GPU, these are terms that I think people are familiar with. But I have a kind of glossary here of some things you might not know about. So FPGAs are field programmable gate arrays. If we think about a CPU as kind of like a generic processor, FPGAs are maybe one level more generic. They're generic to the point where you could put a processor into an FPGA. You could program a processor within this programmable field of logic. Reconfigurable, so you can, rewrite it over and over again. ASIC is another term you might have heard of, or maybe not, which is application-specific integrated circuit. So you can think of like a CPU or a GPU as kind of an application-specific integrated circuit compared to an FPGA. A GPU would be something like, graphics-focused. It's not necessarily reconfigurable. You can't change the way the logic works after you've manufactured it. The subject of this talk is machine learning accelerators. So this is a term that I think maybe not everyone is familiar with as well. But every device that we use today is full of accelerators. Every time you go to a website, it's TLS encrypted. So we have cryptographic accelerators in all of our devices. Every time you go on YouTube, you're streaming compressed media. So again, all of our devices often have specific hardware for cryptographic acceleration, compression, network processing, graphics, motion. Apple always talks about their neural engine. So these things are all either ASICs They're part of the hardware itself. They might be coprocessors. They might be FPGAs. They might be embedded in something like a network card. And I think you see a lot of news, especially with the kind of AI hype, about like data processing units. So these types of domain-specific, maybe reconfigurable, maybe not, application things to make things go faster or use less energy, they're all over the place. Another term, kind of system on chip. Every device, or vast majority of the devices that we use today are also system on chips. So this is from Apple's presentation, like a week ago, of their M4 processor. So we can see, I know the font is like, I can't even read it, but we have kind of CPU sections. We've got two different types of CPUs. We've got GPUs. In the bottom left, we've got the display engine. On the bottom right, they're highlighting the neural engine. So a modern processor is just a bunch of different application-specific subcomponents or coprocessors or accelerators. So all of these things, all these types of devices that are a bunch of different discrete functions bundled in one are systems on chip. And you might be familiar with some of these companies. So the main kind of FPGA and SoC manufacturers are going to be what used to be called Altera, but is now Intel, but is going to be Altera again soon. Xilinx, which is owned by AMD. Lattice Semiconductor. And then there's many more, Microsemi, QuickLogic go in. And maybe, if you took a college class on something like this, maybe you programmed a Cyclone or a Zinc or something like that. But these are just kind of like the glossary of terms that you might see as you start to dip your toes into hardware development. Kind of like GPUs, where you have your GPU manufacturer and then you've got the people who make the actual card. We have the same setup with FPGAs and other programmable logic. So Xilinx might make the FPGA, but maybe Ant Micro or Digilent makes the card. So I have this board that I'm sure no one can see, but that's running on the front here is a Digilent board. The other one here is maybe a Thoracic board. So it's a very vibrant ecosystem, lots of different manufacturers. It's a little tricky to navigate. And by the end of the talk, hopefully I'll make some pointed suggestions for where to get started. So I think probably most of the audience is familiar with like what it takes to build some software as far as designing it, testing it, et cetera. In the hardware world, it's pretty much the same, right? So there's the development of the logic designs that we have to build. There's simulations of how those things will work under real world constraints. The FPGA can only run so quickly. There's obviously like logical testing. So we kind of bundle under the terminology of verification. Synthesis is basically going from your design to something that you could potentially write onto an FPGA. And remember, they're reconfigurable, so you can reflash different designs onto your FPGA over and over again. Or if you were building a chip, that's the same type of thing. You would kind of produce your design to be manufactured onto the chip itself. There's the process of actually like not really for FPGAs, which are these kind of higher level reconfigurable devices. But if you're trying to manufacture a chip, that's a whole kind of own category of things. So integrated circuit design, VLSI, which is very large scale integration. These are all kind of parts of the process. And SoC building, which I highlight just because it's part of development. So again, like these are languages you might be familiar with that you can use in the hardware world: Verilog, System Verilog, VHDL. You might have heard of System C, Chisel, Clash, MyHDL. I'm going to highlight MyHDL, Amaranth, and Migen because these are all Python-based. So these are essentially Python libraries where you use Python to describe the way you want your logic to be built. So it's the bottom 5 or so are kind of fully open source, languages or platforms. The top 3 are more specifications that might have implementations or compilers or something like that. Unlike the software world we know and love and the Python ecosystem that we know and love, the hardware world is still in transition, so a huge portion of the tools that we rely on are proprietary. This isn't like a political talk, but I've highlighted at the right here, the P for the proprietary tools from some of these different companies. But one interesting development that's happened really like in the last, I'd say 10 years or so, is tools like Verilator and CocoaTB. CocoaTB is a Python framework for testing hardware. They've really established themselves as like industry standard tools. And they're like a key part of the ecosystem and kind of slowly chiseling away at the proprietary wall. I think that like the ecosystem that we have in the hardware world is kind of similar to 90s-ish software world. So it's really exciting development to see a lot of these tools emerge as like industry standard. Here's a bunch of synthesis tools. Again, a lot of proprietary tools from the various manufacturers. Tools like Vivado and Quartus, you can often download for free. You can get an education discount. You can use it, just on your computer. And for the stuff that I'm building today, or that I had previously built prior, but I will demo today, I used Vivado for it, but it did cost me $0, which was great. But again, we have some emerging tools like Yosis that are really establishing themselves as, industry standard and kind of cutting into that proprietary wall. This talk is not about integrated, like building chips. There's a lot of those that happen, and I'm not an expert in this. My expertise kind of ends at the FPGA level, but Google and Skywater and these other companies, eFabless, Antmicro, have done a ton of work so that, like in 2024, you can actually go from using only free software to getting something that you can fabricate on a chip, and they will pay for a lot of those costs for you of the actual fabrication, so you can submit a design, get it accepted, and get back, your slice of a wafer with your design and hardware on it, which is like incredible that you're able to do this. And this has been something, again, that's really emerged over the last 5 years or so. It is a relatively large process, so it's like 90 nanometer plus, but just the fact that you can do this is incredible. And SoC design, which I'm going to talk about some of these tools today as well, is something where there's a lot of really, really exciting things that you can do. Both of these are Python-based, like entirely Python-based, for building hardware designs, for putting your own code onto a bunch of these devices that I have here in front of me, which I'll show you in a second. And that's incredible. The fact that we're able to do this definitely wasn't possible 10 years ago, and it's really exciting to see where we're going. Okay, so I'm going to give a couple of perspectives at the end. I kind of already gave them, but I think the TLDR for this is that still an ecosystem in transition, but emerging as a place where open source software is competing with or replacing proprietary software. Not totally, but we're getting there. And Python is playing a key role in a lot of those libraries. So what can you actually do in 2015? That's when I kind of stopped having access to a lot of these expensive vendor tools. The answer was kind of not that much. But a couple of years ago, I started to kind of get back into it. I had a couple of these things lying around. I ordered a few more. I was inspired by, I should note that, many of these community leaders in the open source Silicon ecosystem, the maintainers of these libraries, are just like prolific and incredible developers. So being inspired by them, I didn't write any of the software that I'm demoing today, so I'm going to take all of the credit for it. But they've just done an incredible job. And in fact, in 2024, you can do a lot. And I think one of the key things is you can do a lot for not a lot of money, which I don't think has really ever been true outside the last couple of years. So if you're building designs for these devices, the very first thing you need is one of these devices. So, obviously you probably have a GPU in your device already. You probably have a CPU in your device already. You might have an FPGA in your device and not really know it. But for these things, you probably need a development board. Unfortunately, they're kind of expensive still. I call these like the school boards. So these are the ones you might have used in class by different manufacturers. The top one's a Xilinx one, the bottom one's an Altera one. But actually, I figured someone would yell at me. This is PyCon. I haven't talked that much about Python yet, and the talk description specifically said less than $200, so fine. So it's probably time for us to talk about PYNQ, which is a really, really cool project. Again, it's been like a continual source of inspiration, and I finally got enough cool things together to write a talk about it. So PYNQ is a project started in 2016 or so by Xilinx, which is one of those major FPGA manufacturers. And it is essentially Zinc, which is their system on chip of an ARM processor combined with an FPGA fabric. So you get a traditional CPU with some reconfigurable, reprogrammable logic, and Python. Python is kind of the primary library language for all of the stuff that you use when you interact with these devices. When you interact with the FPGA, you're doing it all through Python. They have extensive documentation. There's a great forum. So again, I know you can't click a link in the middle of the talk, but if you have it locally and they're posted at that QR, those will bring you there. This is just kind of a block diagram. You don't have to know what any of these acronyms are, but the key takeaway is this block in the middle is an ARM processor that you can just, Python is pre-installed, Jupyter is pre-installed. When you turn on the device, Jupyter starts up. along with the PYNQ Python libraries. And you have access to this FPGA fabric. And you're able to, there's a little box here that says Accelerator. You're able to build your own custom hardware designs, put them onto that logic, and then interact with them from Python. This is the one I like. It looks like this. It's about, I don't know, 6 inches wide or so. It's from a company called Tool, and it is the PYNQ Z2. It's a reasonably large FPGA, enough for you to play around with some different designs on it. And it does come under that critical threshold of $200, so I kept my word. I have a Z1 running here, which is a slightly older model. Both of these you can get at an education discount if you're a student or a teacher. But even if you're just a hobbyist, it's still a little bit of a high barrier to entry. There are devices that are cheaper, but I think this is a really good kind of getting to know hardware design, starting to build things. They really make it easy. This is the TLDR of like the Python code. It's a little tricky to follow, but we can see that kind of PYNQ Python library. The key takeaway here is that this is a synthesized hardware design. This is some logic that we've built. We took something, we either wrote it in a hardware language, or we took something in Python and we compiled it into hardware, which is what I'm going to show you in a second. We allocate some memory. We have some NumPy types here, and then we are able to kind of map that between our actual hardware device and the ARM processor, the Python process from which we're running. We're able to send data back. We can send data over to that design, have it do whatever it's going to do, read that data back. So I saw this a couple of years ago, 5 years ago or so, and I was like, wow, that's crazy. Like, one, the fact that it's in Python, the fact that it's using NumPy, the fact that it's made it so easy for you to interact with these designs that you built. So, if I want to raise VC money or get accepted to a PyCon talk, I probably have to make it a little bit flashier than that. So I decided to see if I could take a machine learning model, and again, I'm not that great at machine learning, but take a machine learning model and see if I could put it on the hardware and then interact with it from Python. Right? Hardware should theoretically be faster than kind of general purpose computing like a CPU, potentially faster than a GPU, though not like a super intense GPU, but it should be possible for me to do this. So what do I need? Can I get by with just Python? I think the can I get by with just Python is critically important, because if I don't know Verilog or something like that, it's going to make it that much more difficult for me to get started. So I'm going to use PyTorch for modeling, kind of good standard in 2024. A lot of these libraries will use ONNX as an interchange format. So it's Open Neural Network Exchange, I think is what it stands for. And I'm going to use 2 cool libraries from Xilinx. One is called Brevitas, and the other one's called Fin. Brevitas is a library for doing quantized neural networks. When we're building hardware designs, we don't necessarily want to be doing things in full floating point. And Fin, which is really the key, the central element of this talk, is a compiler, basically, to go from a neural network design in ONNX into hardware. Right? So I can use these 4 tools to build a machine learning model, compile it into hardware, put it onto my device, and then I can interact with it from Python. I am going to use Vivado for synthesis. I'm not going to do it now because it takes a little while to run. So technically, the total cost of software for this talk, thanks to Xilinx commitment to open source software and the vibrant community, is $0. And I apologize in advance because it's going to be a couple more slides of me listing cool technology, and I'm also sorry for overusing this template too much. So that's enough memeing and time to get to the code. So I don't usually trust examples. I'm not great at machine learning, but I don't trust examples, so I wanted to build something from scratch. So given a sine wave, apart from some errors due to like this quantization that we talked about, going from full floating point to potentially 8-bit integers or something like that, some sampling, if I give it like a full period of a sine wave, it should be able to predict the next point, right? I shouldn't have to do that much modeling to be able to do this. So this is a little picture of just like a training set and a testing set for just a basic sine wave. This was the little torch model that I came up with. It's not very interesting. It's 2 linear layers. I think you can instantiate it with a variable number of neurons, but we did 4 when I was testing around. This would be good on its own. You can run this, you can train on that training data sine wave, test it on the testing data sine wave, and it should be perfect. Because we're going to hardware, I swap out the vanilla torch stuff for a quantization-aware stuff from Brevitas, which is that, again, Xilinx library. So it looks mostly the same. If you've ever seen a torch model, you'll be embarrassed for me because this is highly simple, but it's the best I could do. So we specify some things like the bit width we want to use, but basically a pretty straightforward model. You train it in software, and you export it into this quantized ONNX format, so one line of Python code. You then use Fin to build that design for the board that you want. In this case, I did a Z1. The Z1 and Z2 use the same chip. And this tool will actually go through all of the steps that you need. Things like tidying up your design, streamlining the various components of your neural network, quantizing things, converting different portions to hardware, synthesizing any code that you need, generating the actual binary that you're going to load up onto the FPGA. It even makes a Python and NumPy-based driver for that design, which you can load up onto your Zinc processor. And you run this, and it will run it off that ONNX file. So everything was kind of smooth sailing so far, and it worked pretty well. It output that bit file that we can load up onto the FPGA, a Python, NumPy-based driver, some utility functions, some benchmarking functions. Not everything might be synthesizable into hardware. So one of the examples for my sine wave predictor was there's a multiplier at the end that you have to apply back in software to kind of go from fixed point back to floating point. But I got this bit file. It all worked great. I instantiated my accelerator on this PYNQ device, and then I fed it some testing data, right? Just gave it slices of the sine wave, should be able to predict it. And indeed, it was pretty good. This is a little hard to see, but the purple, the magenta here is the testing set. And when I fed it these batches of testing data, the cyan dots are the predictions. So I was able to kind of perfectly predict, modulus a little bit of quantization error, a sine wave. Then I wanted to do a little bit better, so I added some harmonics to it, and it was no problem. It was able to predict that as well. So I was reasonably convinced that you can go from scratch, a torch model, quantization-aware torch model, and with just a few lines of Python code, build something that you can run on your FPGA, which is crazy. They have some off-the-shelf examples that are much more exciting than mine, so I'll show you one of those now. Let me put it into light mode. Everyone's familiar with this MNIST kind of character recognition data set. So they have a precompiled version of it. I'm running it on this device that's right here in front of me, which hopefully folks can kind of see. So I'll instantiate that accelerator. It's now taking that bit file and loading it up onto the FPGA fabric and giving me back this driver from Python. The images are kind of 28 by 28 pixels. So I can just print out a couple of those using Matplotlib. 7.2 takes a little while because it's a pretty small ARM processor. 72104. And then just like I did before, I can actually, using that synthesized driver that comes out of Fin, I can take that data as a NumPy array, load it up onto the accelerator in the FPGA, execute it, and get back, in this case, the number that it recognizes it to be. So I'll run just those first 5, and we see 72104, which I think is pretty good, 72104. So this step was just me taking that image data, the 24 by 24, 8-bit integer data, loading it up onto the FPGA, and the FPGA doing all the work of actually classifying that image as a number. Now I was pretty convinced this is pretty cool. So I wanted to see a little bit how fast it is. A lot of this stuff comes just from the examples. Let's show you how fast it is. So if you run it through the whole kind of testing set, what did it come to in the end? It was about 93% accurate. And it could do, just this little device, about $130, could do 133,000 images a second, which is pretty cool. I thought that was like a reasonably, I was very convinced at that point that this is pretty easy to do. It's easy to go from Python. I didn't have to learn any hardware design, and it was able to do a reasonably complicated model. So if you've been following along so far, I know I talk a little fast. Hopefully you're also convinced that with not a lot of code, a little bit of knowledge of Torch and one of these devices, you can do pretty fast machine learning inference in hardware. You can start dipping your toes. It's still a bit of a toy, so this space is still a space in transition. You got Raspberry Pi, your computer, some type of large server, a small GPU, a kind of consumer GPU, a really kind of production-worthy GPU. The PYNQ that we just ran here versus one of these, like something that your company could buy. These things are still pretty expensive. So, those very big GPUs are quite expensive. Very big FPGAs are quite expensive. But more and more, I'm just going to skip through this because I don't have a ton of time and it's not particularly relevant. But this kind of zone of a couple $100s is the sweet spot for open source because it's really where all the power users live. So once I had built this design, I wanted to bring it to somewhere a little bit faster, a faster interconnect. I needed a slightly larger FPGA. This metric doesn't really matter, but just something bigger. I wanted PCIe or networking capabilities so that I could talk to the FPGA a little bit faster. I wanted some memory so I could load up more data and have it more directly accessible by the FPGA without having to go back and forth. And I wanted it to be pretty cheap. And again, in 2024, there's a lot of tools that you can get in that kind of next step. After you've started to dip your toes in hardware design, there's a lot of like places you can go afterwards. So this is one of them. It looks like this. It's called Night Fury, and this is a LiteX based board. It's PCIe based. It satisfied all my requirements. But you now have a lot more things. When you start to do more in hardware design, you've got a lot of components. You've got RAM, you've got networking. And this library, LiteX, which I mentioned a little bit earlier, lets you do all of that. You can represent hardware, so you can kind of write your logic. You don't have to learn Verilog. You can just do Python. You can represent complicated systems like on-chip networks. You can link together somebody else's hardware project with your hardware project and put it all on the same device, all from Python. So again, this code is a little bit complicated, but I can instantiate some DDR3 memory, right, interconnect. I can instantiate that PCIe driver in Python. I can load up, in this case, I just took the example, the LED chaser, just turn on the LEDs on the device, all from Python. And I can also do all this toolchain stuff. I can compile it with a Python-based workflow. So this is pretty wild to me in 2024. The LiteX framework has support for like 150 boards out of the box. There are fantastic tutorials, which again are linked from here. Lots of demos and examples. I can't do one today actually because I've already run out of time, but also it doesn't run on my MacBook. But maybe next year, I'm kind of banking on it'll be a little bit nicer and maybe I'll get to come back to PyCon next year. So the takeaway here is basically, just like you can start programming, you can follow a CUDA tutorial. It's accessible now in 2024. It's been accessible for a few years, but you should get started. It's really exciting. It's really interesting. It is a bit harder to do than GPU programming, but it requires a little bit more domain knowledge. But it's there, and it's getting easier and easier every year. There's a really dedicated community of very, very talented people working on all of these things. A lot of these companies, and I think when we start to participate in these ecosystems, the companies are more and more convinced to do things in open source. Xilinx in particular, all those tools, Brevitas, Fin, they're all open source, which is incredible. And I was shocked, as I've been going through this the last couple of years, how far it's come, and the fact that there are all these wonderful Python-based, what I call like on-ramps for you to get started. You don't have to know a hardware description language. You just need to know Python. Yep, sorry. These are a bunch of cool other projects that I think you should check out. Yosis, Amaranth, Chips Alliance is a great organization spearheading a lot of this open source development. The Fast Machine Learning Lab is doing a lot of this stuff. They have a project called HLS4ML, which is basically, I don't even want to write Verilog, maybe I don't even want to write Python, I can use C++ or something like that to kind of describe my hardware, and I can go from a relatively software-y C++ design into hardware. You've got things like Glow, which is a PyTorch kind of same deal model to hardware compiler, XLS, which is a Google, again, kind of high-level language to hardware compiler. ESP, which is a really cool platform of taking a bunch of machine learning accelerators and putting them all together on the same device. And again, I'm not an open source silicon expert, but if you are interested in like fabricating your own chip or getting your design into one of these projects, the free and open source Silicon Foundation is also a great org to follow, and Tiny Tape Out is a really, really cool project where you can, that's what I said before, where you can basically get your design on a chip. Cool. I know I don't have a ton of time, but thank you again for staying to the last session, and I hope if you take anything away from this talk, it's that you'll go follow those repos and you'll try and get started, and hopefully you'll realize it's a lot easier than you thought. Thank you. I don't know if there are any questions, but I'll stick around, and if anyone wants to poke around some of these devices, I'll stick around afterwards as well. No, I'm not, but I'm kind of around, like in the digital sense. So you can always find me, and I've got a bunch of these projects have a lot of stuff that they've got going on. I don't lead any of them. I'm just a contributor to them. But if you are interested in this stuff, there's a lot of forums, and yeah, it would be great to have people who are interested to contribute. Oh yeah, sorry.
Yeah, I noticed that you mentioned Amaranth, and you didn't really touch on it, but
Yeah.
you had a lot of ground to cover here, and you did a great job. Have you messed around with Amaranth?
Oh,
at all?
yeah, for sure.
I'm a huge fan of Catherine White-Quark's
Yeah.
work. Just incredible, prolific.
Oh yeah,
developer.
I mean the people in the open source hardware ecosystem are just
Yeah.
some of the most talented developers
So
you'll ever meet. It's
if you
crazy.
can, I guess, just what have you done with Amaranth? Are you working specifically in this accelerator space, or are you working on other things
so
with
a
Amaranth?
lot-
I'm
Amaranth
mostly
Light-
familiar with it because of Glasgow. So
Yeah, oh yeah.
Yeah.
So Amaranth and LiteX kind of do some similar things, and they're similar projects. I just happen to, more of the devices that I was working with were kind of already working in the LiteX space, but Amaranth is kind of like the next generation. It's a rework of the hardware descriptor language underneath. It's a rework of a lot of the SoC design stuff. So I just haven't had enough time dedicated to learning it. But since I know LiteX, thankfully, it's a fairly short bridge. But yeah,
Great.
the project is fantastic, and they're moving so quickly. They do a ton of WASM stuff, which is
yeah,
they're
I've been
putting
seeing
all
a-
of
I
these
saw
synthesis
Yosis was on
tools
here as well.
in
Yeah, yeah.
WebAssembly. So
Maybe you can talk about it another time.
oh yeah, I don't want to steal her thunder, but you can do all the FPGA synthesis in your browser via WebAssembly, which is crazy.
Cheers.
Yeah. Oh, sorry.
Hi. I know very little about FPGAs. I was wondering if you have any experience or if it even makes sense to kind of compare the performance hit that you get out of using this high-level language to hardware design compilers. I don't know. The thing I have in mind is you either write hand-optimized assembly or you trust your compiler. Nowadays, most compilers are very, very optimized. What's the situation from that point of view?
Yeah,
now?
this is so within the hardware design community, I think there's maybe a spiritual disagreement. So when you use an HDL, which is a lower level descriptor of the things that you want to produce, there's an idea that it's faster. So even if that HDL is in Python, you're directly describing the hardware that you want to design, so it should be faster. The kind of high-level language to low-level language compilation is called HLS, which is high-level synthesis, and those compilers are getting really, really good. So the actual model synthesis that Thin uses a combination of hand-rolled RTL designs and some high-level synthesis designs. There's always one fly in these places. I didn't really notice a performance hit. The design that I'm doing is a combination of the fast stuff and maybe the slower stuff. Mm-hmm. But in today's day and age, I think a lot of times, unless you have a very, very, very specific thing you're trying to do, the HLS tools can be pretty good.
Okay. And if I wanted to research this more, what kind of HLS performance would be a good
There's
search?
a lot of papers on it. I think it's tough because some of the HLS tools a lot of them are proprietary.
Right.
But in this one, so XLS is a great place to start. It's a Google project, so it's got a ton of contributors. It's got a ton of stars on GitHub. That's definitely a good place to start if you're interested in this type.
All right. Thanks a lot.
Yep.
Can you show the board that you were recommending for LiteX?
Oh
again?
yeah, sure. He just released it actually a couple weeks ago. So this is an old crypto mining project that kind of became defunct. So you can get these for pretty cheap. This is a kind of similar one. It's a reasonably sized FPGA, and there's two types of boards on this project. Internet's a little slow, but you can also buy an off-the-shelf board from one of those other manufacturers, and it's almost certainly already supported by LiteX. Yeah.
Cool. Thank you.
Other questions? Cool. Thank you, guys.